Introduction to chemical bonding. A chemical bond is the attractive force that holds atoms together to form stable molecules or compounds. Atoms bond for two primary reasons. First, to achieve a lower energy state. Second, to satisfy the octet rule by filling their valence shell with 8 electrons. There are three primary types of chemical bonds: ionic bonds, covalent bonds, and metallic bonds. Ionic bonds form through the complete transfer of electrons from one atom to another. This typically occurs between metals and nonmetals with large electronegativity differences. Covalent bonds form when atoms share electrons instead of transferring them. This typically occurs between nonmetals with similar electronegativity values. Metallic bonds form in metals, where valence electrons are delocalized and shared among many atoms, creating what's called an electron sea. Understanding chemical bonding is crucial for predicting molecular properties, explaining reactivity, designing new materials, and understanding biological systems. This concludes our introduction to chemical bonding. Next, we'll explore covalent bonds, electronegativity, and dipole moments in more detail. Covalent bonds form when atoms share electrons to achieve stable electron configurations. For example, two chlorine atoms can share a pair of electrons to form a chlorine molecule. There are two main types of covalent bonds: nonpolar and polar covalent bonds. In nonpolar covalent bonds, like in a fluorine molecule, electrons are shared equally between identical atoms. In polar covalent bonds, like in hydrogen fluoride, electrons are shared unequally. The more electronegative atom, fluorine, pulls the electron density closer to itself. Electronegativity is a measure of an atom's ability to attract electrons in a chemical bond. Electronegativity increases from left to right across a period and decreases down a group in the periodic table. For example, fluorine has the highest electronegativity at 3.98, while hydrogen has a much lower value at 2.20. The difference in electronegativity determines whether a bond is nonpolar, polar covalent, or ionic. A dipole moment occurs when there is a separation of charge in a molecule due to the unequal sharing of electrons. The dipole moment is calculated as the product of the magnitude of the partial charges and the distance between them. Water, H2O, is a classic example of a polar molecule. It has a bent shape with oxygen at the center and two hydrogen atoms. Oxygen is more electronegative than hydrogen, so it pulls electron density toward itself, creating partial negative charge on oxygen and partial positive charges on the hydrogens. Due to the bent molecular geometry, the individual bond dipoles do not cancel out, resulting in a net dipole moment pointing from the hydrogens toward the oxygen. Carbon dioxide, CO2, is an example of a nonpolar molecule even though it contains polar bonds. Each carbon-oxygen bond is polar, with oxygen being more electronegative than carbon. This creates partial charges and individual bond dipoles. However, due to the linear molecular geometry, the bond dipoles are equal in magnitude and opposite in direction, so they cancel each other out. As a result, carbon dioxide is a nonpolar molecule overall. PFAS, or per and polyfluoroalkyl substances, are known as forever chemicals due to their persistence in the environment. These compounds contain extremely strong carbon-fluorine bonds, which are among the most stable covalent bonds in organic chemistry. This molecular stability makes PFAS resistant to natural breakdown processes, allowing them to persist in the environment and accumulate in living organisms for decades.